So let's start. So the first theme I want to talk about is perhaps amusing. So gradient, curl, and divergence. These are words you've perhaps heard before, and this is a translation of things I've been doing into things that are familiar in physics. I want to make sure you understand the translation. So, first thing we'll talk about is gradient, just to be sure. So gradient is a concept that is not defined. It is only defined if you have a metric on the manifold. But let's start from the classical situation. The function on some domain in Rn, some open domain in Rn, real value function. And let's assume 0 is in this domain. And I'm looking at the set f equals 0, 0 set of the function. And I assume, which you all know by now, that, so 0 is no particular point, it's just a general point. Assume that the differential of which is defined, it's a well-defined notion, df, say at 0 is not 0. Oh, let's make this point any point. So let's make this p 0. Just so we don't get confused with 0 being 0. Now the rank theorem says, says that there's a diffeomorphism of U, so here's U. There's a diffeomorphism of U, let's say, onto a neighborhood of 0. This time I normalize and make it 0 in Rn. Say this is the x1 axis. And from now on, the remaining axes, so to speak, the remaining variables, I call it x prime. So there's a diffeomorphism that maps U onto, say, so U here is will go on to some set here, V, perhaps after shrinking, so that the original submanifold f equal to 0, which was here in U, is f equal to 0, is mapped onto x1 equal to 0. Yes. So it says that, okay, I'll write it here, this f equals 0 corresponds with this mapping to x1 equals 0. Now, it's completely intuitive, I feel, that orthogonal to, see, there's no metric here, but intuitively anyway, here's x1 equals 0, and the normal direction is orthogonal to that. That's the tangent vector, if you want to write it, ddx1 at 0. Is somehow orthogonal to that, and one should understand that this should be orthogonal here, whatever that is. So this is completely obvious to a child, that if you have a plane, that's a plane. And this is naive geometry in RN, although there's no metric, we have this naive geometry. Somehow there should be something here that many people would call the gradient. So I'm going to write it here. So some strange thing called the gradient vector. So the gradient of f of p equals 0. As I said, this is not defined. I want to repeat that. The gradient is not defined. It requires additional information to define it. So what is this additional information that is needed? Let's discuss this matter. What is really the gradient? Well, I'm going to draw another picture. I'm just showing you all the pictures I have in my brain. There are very few. This is f equals 0. Here's the point P0. And in there we have curves. So curves define tangent vectors. Let's say the nice color here. So we have some curve here. Some curve. Well, a curve, as you know, is a map of an interval, say gamma, into the surface. And you want to set this thing up at P0, so gamma of 0 equals P0. And the curve has velocity vector, you know. I mean, here we have this standard field here, and that transports here to velocity. Okay? And as you know, curves define tangent vectors, so the tangent vector associated with this curve is computed in the following way. You just take a function, say some function h that you want to differentiate, and what do? You just differentiate it along the curve. So that defines the tangent vector at this point. Okay. Now, that's the tangent vector. That defines a curve. So for any function, any h defined near this point. Say we're in Rn someplace. Well, where are we? I said we're in U. So I can tell you how to differentiate any function with this curve, not just a function defined on this submanifold, any function. Now what happens? Well, I took the value 0, but any value. Let's take the value 0 again. It's completely clear that if I apply that to the function of h, so h gets h as above with gamma of t contained in the level set of f. So you take a curve in the level set and you differentiate it. This is completely stupid. You get 0. I mean, the curve is constant. The function is constant. It's 0. It could have been some number, like 20. No. It says that any curve like this, and curves define tangent vectors, so the tangent space at P0, let me write it out long, of this submanifold F0, it's defined by all these curves. Yeah, it defines it by all these curves equal the curves modulo equivalent. So it equals the set of tangent vectors V in the tangent space at P0 to U, such that, well, what is this condition here? Let's write this. This is df of the velocity vector. So it says check what I'm writing here is correct, such that df of the velocity vector, so that's you can arrange for any vector to be a velocity vector you want, so that this is equal to 0. So you agree with me that if I take a curve and take the velocity vector for a curve, the curve is in this thing, f is constant, I differentiate, I get 0. That's one direction. Conversely, if I take, well, converse, you can just check by all sorts of things that this is exactly what you get. That is the tangent space. You see, there is no gradient. I don't see a gradient there. I'm looking at this blackboard, I don't see a gradient. I see df. Okay? The gradient is not defined. df is defined. Okay? Now, take the standard coordinates. So take standard coordinates for Rn. Say x1 through xn. And the velocity vector in standard coordinates is some v minus, as I say, constants at this is now, okay, x, I don't know, x equals p0. And that's a velocity vector, and df is some, what is df? Partial f, xi, well, in general, dxi, at the point we should evaluate. So, df at the point p0 of v, it's not very hard. You put v in here. You put it in here, right? And of course, this basis is dual to that, so that's just nothing more than sum of at df xi. Let me be precise here. At the point of question times v. And that is, of course, the standard inner product of the gradient of f at the point p0 with this, the standard inner product. So if you compute in coordinates, but you see coordinates forced us to take a basis ddx1, ddx2 for the tangent space, and dx1, dx2 for the dual space. You see, it forced a metric on us. Because this basis here is dual to that basis here, and the metric is just exactly that. It identifies a vector space with its dual. So it forced the standard metric on us. It forced it. The thing you learn from this is the gradient vector or gradient field is dual to df in the standard metric. So, gradient is existing. Here it is. Let me write it again just for the record. The gradient of f is a vector field. I've evaluated it here. Arose via coordinates and in reality via the duality between ddxi and dxi. So the next time you see the gradient, you better hope that either you're in some standard situation like Rn, or somebody has given you a metric. So let's be precise about that. So let mg, we don't need a Riemannian manifold for this, but I'll say Riemannian. You can have Lorentzian manifold here. So I only need the fact that the pairing is non-degenerate, but let's just assume this, let this be a Riemannian manifold, as an example. Okay, I'm going to go through this discussion very quickly and really clear up this business about what really is a gradient. And in order to have a gradient, we need a metric, and I assume that we have a metric on a Riemannian manifold. Okay. Now, as you know, let's go back to linear algebra minus 1. Linear algebra minus 1, not linear algebra 1. Linear algebra minus 1 says that if you have a non-degenerate bilinear form, so G defines an isomorphism. Now I'm going to be a little bit morphism. From the tangent bundle of M, let me call this isomorphism phi G. Phi G is an island. But this is an isomorphism. But the girls on Fiji are much more beautiful than around this. So this defines an isomorphism. I think I want to go this way. Namely, phi, let's see what happens. Phi G, I have to apply it to a vector, is the form defined by G V point. Right? A vector defines a functional. And of course, I have not written this explicitly, but this is a point, maybe let's write it explicitly, over a point P in the manifold. So we could put the point P in the manifold. This is a tangent vector over the point P in the manifold. And this is then the metric at the point P in the manifold. And this thing is in the cotangent space at the point P in the manifold. So it says if you take a vector Vp in the tangent space of the manifold, you get a covector in the cotangent space. And this is a bundle mapping. It's a bundle isomorphism. So this gives us a bundle isomorphism of the base. It doesn't do anything on the base. So it really is an isomorphism. Now I warned you that the tangent bundle and cotangent bundle are totally different things. But now, in this lecture, I provided you with an isomorphism. On the other hand, I needed a metric to do it. Okay, that is the definition of a metric, well, a non-degenerate bilinear form. I didn't use the positive definiteness here.
So, what properties does your isomorphism have here? I mean, it's not only a bijection. It's also
It's a bundle isomorphism in the sense of bundle isomorphism. So it's a smooth map, which is linear isomorphism on each fiber. That's, yeah. And you can just check it here. I mean, it's completely clear. It's smooth. Everything's perfect. Okay. And now, what is some person hands you a function. Some person says, "Hey, I've got a function for you. Tell me about the gradient." Right? Now you can do it. So, well, what is df? df is a one form, and a one form is a section of the cotangent bundle. Right? At each point, it's a cotangent vector is a section of the cotangent bundle. Well, that gives us a map here. Right? If you want me to be explicit, I have to tell you what this map is here. That's a section. The map is, take this section and go back here. This is an isomorphism, so I can do it. So gradient of f corresponds to df with the metric, and the precise statement is you take df and then you pull it back with this isomorphism. with a standard metric. It's an easy calculation. A standard metric that we discussed here with the standard coordinates, you get the standard gradient. Okay. We've talked about Lorentzian geometry. I didn't use anything positive definite here. This could have been a mixed signature form, right? I just used this isomorphism, which requires that whatever it is, there is an homogeneous. So that's great. Okay. And in a very real sense, you see, if you have this diffeomorphism between here and here, this thing is orthogonal here. Well, in a very real sense, it's orthogonal here. And if you check the tangent space, I mean, here's the tangent space of this thing. This is the orthogonal complement at that point of the gradient. See, the gradient is the tangent vector. The manifold has a metric, so it makes sense to talk about the orthogonal complement. And the tangent space to this submanifold is the orthogonal complement. Let me underline this, with respect to whatever metric we chose. So with your eyes, if it's some crazy metric, maybe with your eyes you think it goes over here, but that's just a metric. This is fundamental to really get that straight, okay? There is no such thing as a gradient, period. If you have a Riemannian manifold, there is a thing such as a gradient, and it's associated to d of a function by the canonical isomorphism defined by the metric, but the metric is not canonical. Okay? In fact, in physics, in some sense, what you look at something weaker than what I'm going to say. You look at the space of all metrics. Yes, you really use these huge spaces and the space of all connections. Okay? So please remember that. Okay, I do want to say one more thing. Let's continue in this vein. In anybody's work in analysis, you have domains D. So D is an open set, a domain, connected, open set in some manifold. Okay. And we have reasonable domains which are defined by smooth functions, being a set of points where a smooth function is less than 0. Zero, I use 0 all the time, you notice. Less than some number, it doesn't matter. The inequality less matters. If I put greater, every sign will change. Okay, so I mean less than a number. Okay? So quite often you will have domains that are defined this way by a smooth function on the manifold. Okay, so you have some domain, and inside the domain here, f is negative, and your intuition should be outside, f should be positive. And f should be 0 on the boundary. Right? That's what you're feeling about a good domain like this. Okay. So the boundary should be given by, the boundary of this domain should be given by f equals 0. And f equals 0 can be catastrophic, as you know. It can be any closed set. So if you're doing all sorts of complicated dynamics, which some people here do in this university, the terrible sets occur in that regard, but we don't do these complicated dynamics and so on. We just consider the situation where df, here we go, restricted to the boundary of this thing, is nowhere 0. This is the smoothness assumption. If df is nowhere 0, right, df nowhere 0, that says you can transform this domain locally. I'll draw the picture. You're at some place here, at some place P0 on here. You have something here. There's a diffeomorphism which transforms this domain into this picture, x1 equals 0. Yeah? And so this piece of the boundary gets smoothly transformed into something like this. Okay? Yeah? So if locally it's beautiful, it may be a complicated boundary, it may not be a sphere. I don't mean to indicate that it looks like a sphere or something. It could be very complicated, who knows, but at least locally, at least it's smooth. That's the usual. So this means we just say when we have this is a domain D with a smooth boundary. We do analysis on these kind of domains. As you know a bit from other subjects, you solve different partial differential equations, for example, with boundary conditions like Dirichlet problem, Neumann problem, and so on. So smooth boundary, yes.
But as I can imagine, in my stupid brain, isn't this like really rare? That I mean,
no.
For example, I mean,
The standard.
the sphere doesn't satisfy this, right?
Sure it does.
It does.
Globally, you don't have to think. I'm going to answer your question and maybe help you a little bit. The sphere is defined globally by the norm function. Norm equal to 1. So norm squared minus 1 equals 0. Okay? Now I've written this, that answers the question for the sphere. I mean, maybe you're still dissatisfied. But don't forget, you only need the condition locally at every point. Because what you can do is, maybe you don't have a priori you don't have the function globally at first. But then locally you can pave out here, and then with the partition of unity you can build the function globally. Okay? So it's really not a heavy assumption. It's really a standard assumption. Okay? And for all partial differential equation questions, originally you will find this kind of thing. And the minute you have possibly boundaries are not smooth. But the standard weakening, for example, for applied mathematics, for the finite element method, for example, you will have at least some smoothness, like piecewise smooth boundary. And even if you have these boundaries which, for example, you have the Navier-Stokes equation, something like this, and you're interested in understanding a lake, the water on a lake. It's a very tough differential equation. And the boundary of a lake can be just horrible, right? But it's piecewise smooth. Okay? And one of the big artistic works, it's almost like, what? These scientists in the old days who didn't understand what light is, and they thought it was little balls running around, and what were they? There's a name, I don't know. These mysterious scientists, It's almost a work of art to really understand how to triangulate these complicated boundaries. So quite often, we assume that at the singularities of the boundaries, they're transversal. So not smooth, generally smooth, but maybe at the corner, there will be some corners, maybe finitely many, and then transversal. That means the tangent spaces here are transversal. So for any analysis problem, you will have something like this. I guarantee you, at least until you get in high-level subtle problems, you will always have this. And if you don't have this, the first step is to approximate by this, and then hope that the approximation goes through in some sort of way. Okay, so this is a smooth boundary. And what everybody knows about here, and you've seen it in your applied mathematics courses, even in the notation of Green's theorem and so on, is you have a normal vector field along the boundary. Right? A unit, for example, unit normal vector field around the boundary. Everybody thinks of this normal vector field around the boundary like that. So some normal vector field. Now, a normal vector field doesn't exist without further information. As you know, from high school geometry, a perpendicular depends on your choice of the geometry. So what is being discussed here is the gradient field along the boundary, assuming you have a metric. Now, it's no assumption, because you have many metrics, and for many applications, it doesn't matter which metric you have. You just take one, and maybe the angles look different optically with your eyes for one metric or another, but you take a metric. So take some metric, and then gradient of f a normal vector field in the above sense. And it really is normal, it's pointing out. It's pointing out. Okay? And in fact, if you normalize the one parameter group, so GT, so you take this normal field and then you extend it to some neighborhood just by extension in trivial fashion. If GT is the associated, is the one parameter group locally, of course, locally near this boundary of some appropriately normalized field, you have to normalize the lengths of these fields to get this to work. Normal field. You're going to love this. You're going to really like this. If you appropriately normalize the field, then you have the one parameter group acting, and the integral curves go out. Here the local integral curves going out here along the boundary. You go out, you go out, you go out. This boundary is where f equals 0. All right? And the theorem is if you appropriately normalize the length, make it like 1 or something like this, then look at this. F composed with g of t equals t. You see what happens? It's beautiful, isn't it? You see what happens? At time 0, you're along here. Then you flow with this one parameter group of this vector field, and at time t, you go out here. That's the nearby level surface. You push with a vector field to the nearby level surface on the normal flow. Okay. That's a fundamental thing to understand. Okay? It's not canonical. You choose a metric, you have the gradient pushes out, you extend it a bit in the neighborhood, you normalize appropriately, you have to where the velocity here is 1, and then push it on out, you get this. In case I will tell you, this is fundamental for elementary Morse theory, right? I mean, you have to push from one level surface to another with the flow. Okay, I wanted just to comment. I've said enough on gradients. I've harassed you with gradients. Okay. Now I want to go to the funniest, so a translation of the Durand. So a funny translation of the Durand complex. And I'm going to do this in a simplistic way in R3. So we can have some fun. Let's have some fun with the Durand complex. Ready? So here's the Durand complex. You have the constant functions on R3. You have the functions on R3. So I don't write R3 all the time. Yeah, let me just say n is equal to R3. The constant functions. The one forms. Aha! I have D. I have D. It's a complex because D composed of D is 0. 2 forms, 3 forms, D. 0. Okay? Now, we use a standard metric. So G equals the standard metric. Okay? And underneath this Durand complex, I'm going to write a physicist complex or an engineer's complex, or I don't know whose complex. This is Durand complex. I don't know my history, but just for fun, let's just say I'm going to write Durand on the top and Maxwell on the bottom. These things that occur in electrodynamics, this is 19th century mathematics on the bottom and 20th century mathematics on the top. I'm going from one to the level, and I'm going to explain exactly the translation. I explained some in the notes, but I will explain more. Okay? So here we go. Well, Maxwell knew about the real numbers. No problem. And he knows about the function. No problem. That's the identity. All right? I'm not going to write all these maps. You're going to have to fill the maps. Okay, here we go. Well, here's this operator. Here, aha. What about this? Gradient maps a function to a vector field, and we know how to identify the two. Right? I just did it. I spent a half an hour doing it. Right? I told you how to do it. I said go up to Durand, take D, come back down. From Maxwell to Durand, across by D, and come back down. It's a vector field, right? Okay. Well, that's pretty good. Now I'm going to have really a lot of fun. Now, what I'm going to do is, actually I'm going to make a diversion. I'm going to incorporate another British mathematician named Hodge. So I'm going to, this is a Mickey Mouse version of the Hodge operator, but it's something, sorry that this was too close here. I didn't plan my didactics very well. I'm not very good at didactics. So Hodge is on top of all this, and Hodge goes from here to here. This is Hodge. So this is Hodge. Hodge is a wonderful British mathematician of algebraic geometry in principle, major works pre-World War II, but of course later. And this Hodge operator will be called star. You have some intuition, we've talked about it, that there's some symmetry in this Durand complex, right? This end and this end somehow, these spaces are getting bigger in the middle and smaller at the end and so on. Well, here's how Hodge does it. Now Hodge doesn't, you don't get Hodge for free. You don't get Hodge for free. I'm going to tell you how to go from three forms to functions. From three forms to functions. Okay? Here's how you do it. Hodge needs an orientation. in modern lingo, this guy needs an orientation. I don't know what that means. So, okay, so Hodge needs an orientation. So this star operator that's going to go across there needs an orientation. And now I'm going to tell you what here we will use the standard orientation on R3. Standard orientation, omega, standard, on R3, which is dx1, wedge dx2, wedge dx3. Okay, now why the devil is that an orientation? Let me erase some type. So I'll tell you the definition of an orientation, and I'll tell you why this is the definition. And I'll tell you can't do anything in this subject in terms of analysis. Not really, can't do much unless you have an orientation. Okay? For example, you can't integrate. You have to do some tricks in order to integrate if you want to integrate if something's not oriented. You know one example that, at least intuitively, you know it's not orientable, namely the Möbius band. Let me give a precise definition of an orientable map, of an oriented map. Hodge needs an orientation. forms to one form, so I need an orientation. So definition. M omega is an oriented manifold. Means that omega is a nowhere vanishing element of the top dimensional stuff. So let me emphasize, I'll just put it, well, okay, E and N. Let me emphasize, I mean by this, the top dimension. So this form here, where did it go? Dx1, here. This form here obviously doesn't vanish anywhere, okay? I mean, it's completely clear. This is a 3 form, does not vanish anywhere, okay? Okay, so that's an oriented form. Why is that a good definition? A nowhere vanishing 3 form. You see, this differential form language didn't come to the modern world until really after the Second World War. My friend Matsushima lived in Japan. Chevrolet came to Japan and told him what a differential form was, and he was incredibly happy after World War II. Yeah? It's very, very interesting that this differential form language allows us to give some smooth definition of orientable. You understand, if you take the high school Basel, and you Basel a Möbius band, and you take your usual 2-frame, and I got excited about this in high school, right? And you push this around the Möbius band, and it comes back and it's the other direction, because you think it's on the back of the Möbius band, but the Möbius band, and then there's the stupid remarks about ants going along with these things, right? This is all stupid, right? This is completely not stupid. Yeah? A non-vanishing 3 form. Now, why is that good? Well, how do you say a frame, or N form, a frame, what is a frame of vector fields? Say x1 through xn, say some local frame of vector fields, is said to be positively oriented you stick in these vector fields and see if you get a positive number. If it only is omega of x1 through xn is positive. If I give you a 3-frame in R3, you're supposed to tell me whether it's positively oriented or not. You get it? Do you understand? I give you let's do this in R3 and have some fun, okay? So this is the definition of abstract, and here's the 3-frame. So, well, let's have some really non-trivial fun. So, xj is equal to some aij ddxi. Okay? That's a vector field, right? So we have n of them. On Rn. So I and j between 1 and n. Now we're really having fun. And we're going to use this standard orientation, dx1 wedge dxn. And then we ask somebody what we're going to get here if we're going to put these fields in the standard orientation. Right, we're going to ask whether it's positive. You can put them in. And if you're lazy, you ask a computer to do all this stuff. But you don't need to know because you know the definition of what this is the determinant of that matrix, Aij. And so if you have a frame which is defined by column vectors, right? Yeah, column vectors, let's put them in. You want to know whether those column vectors are positively oriented or not, you just check the determinant. The determinant has 2 signs, plus or minus. You get it? So a frame is either positive or negative oriented. It's key that this form can't change sign anywhere. You see, if you allowed it to be 0, then You see what I mean? It would be 0 there and be negative. You see what I'm saying? It wouldn't work. Okay? There are only 2 orientations on them, at most 2 orientations.
So Professor,
Yeah.
you said that it's oriented then means if you apply the sigma to the x1 to xn, then it's not equal to 0. You mean that? You said the sigma is nowhere.
Well, I don't see
vanishing
sigma here, but
Oh, omega, sorry. Omega is nowhere vanishing element.
that numeric vanishing means at every point it's not 0, which means at every point it is, in this case, it is a basis of the nth exterior power of the cotangent bundle. At every, okay, maybe that wasn't clear. That means that this form, it means in lower, so omega, see, we know omega is equal to, it's a form, so it's a function times this basis. Let me just do it in this basis, okay? And this, and omega at p is f of p times dx1 at p with dxn of p. And to be nowhere vanishing, I mean, this is a basis of the exterior product. I mean, it's really a basis. It means this function is nowhere 0. Okay? It really means this function. So you see, if you have a background thing like this, the only difference you can get is the coefficient function. And then you ask yourself whether it's negative or positive. So you see there are only 2, I think this helps you, right? There are only really, that's what it means, nowhere 0, and there are only 2 orientations. Up to equivalence, obviously. I mean, who cares whether the number in front is 27 or 85? I don't care, right? I mean, it's just whether it's positively oriented or not. So you have, you learned this in kindergarten, also this rule about sometimes the right-hand screw rule, something like this, like that. That is, you have 2 vectors here, and you have a choice of which vector you put up here, and it's exactly, you say, well, I put that one up there, I get a positive number. If I put this one up there, I get a negative number. And you see that if you're going to do integration, which has to do with volume, and this is in some sense measuring volume, that determinant is the volume of the parallelepiped spanned by those vectors, right? You better understand what positive volume and negative volume is, okay? So you better have an orientation, okay? And that's the definition of orientation. And quite often, without saying it, again, there are applied people here, physics and so on, without saying it, what happens in your discussions in your applied sciences is you assume that you have this orientation, okay? It's a useful orientation, I like it. So it all comes from coordinates. As soon as you have the coordinates, you have them. Okay, and now Hodge. I told you Hodge needs an orientation. So star maps 3 forms. What did I guarantee you to functions? Oh, I'm sorry, n. To functions. Well, what is it? Well, I just told you. You're going to really hate me. This is too trivial. A thing here is the standard form times a function. There's no choice. Well, and it's not very clever to map that to the function. Right? So these things are kind of, once you choose this orientation, they are absolutely stupidly isomorphic, right? You just take the coefficient and that's a function. So this is this Hodge operator.
Professor, can I ask a question? I mean,
Sure.
It's an old question, but I didn't manage to figure it out. So when we started talking about one forms a long time ago, we defined them as functionals on the space of vector fields.
Right.
That's what one forms are. And then you said that there is a God-given operator D that sends functions to one forms. But in my head, so the one forms that are in the image of this D are just the ones that are exact. I mean, the ones that are, so you cannot write all the one forms as DF.
Absolutely not. That's right.
But in all your problems, you write all the one forms as DF. That's my question.
Where have I written a one form as DF? None of this. For example, even here, you see, that's not D of anything. I mean, this, here, why is that D of something?
No, I'm talking about one forms now. No, maybe it's...
So D is not isomorphism, or it's
No,
not
it's
subjective.
definitely not.
No, far from it. That's the cohomological obstruction. Kernel modulo image. For sure the image gets killed by the next map, right? And if you have topological obstruction, you may not even have everything in there, right?
So when you talked about gradient earlier, that you use that map because you have the function from the beginning, so you map it to.
Absolutely, that's exactly the point. That's exactly the point. On the other hand, you have very good. I now see why perhaps I also confused you. This map here, that's where you were confused in some sense. Why I confused you? There is this map here from one forms to vector fields, but it has nothing to do with D, right?
It's just you identify
Take the coefficients.
Identify bases with bases.
Yeah, I should. Yeah, exactly. Exactly. It just uses the dual basis. Okay, that's very good. Thank you. Yeah, that's a very good point. Okay, but I think so far this is understandable. What's coming now is really serious. It's also not difficult. Hodge helps us again. Hodge is going to do something. I'm not sure which way I want to go. These things are actually isomorphisms. So let's see here which way. I want to think for a minute which way I want to go. Yeah, I'm going to go again this way. I'm going to always go down. Star. So I'm going to introduce another Hodge operator. These Hodge operators, the way I formulate it, go from top to bottom. Okay. So this is a linear operator, so I want to tell you what it does on the basis. Let's see if you can guess what this operator is doing. So the first basis element I have is dx1, dx2. Yeah, that's one of the basis elements of the two forms, and I need to tell you what star that thing is. And I'm going to call that's going to be dx3. Okay. So it's a guessing game. We can play this game with our mothers, or I can play it with my wife and granddaughter. So, okay, here we go. The star of dx1, dx3 is minus dx2. Getting some feeling. Star. This operator is then going to be linear on the function, so I just need to define it on the basis. Star of d, what I don't have here. dx2, dx3, any guesses?
It's dx1.
dx1. Okay, somebody knows. Why do I put a minus sign in the second?
dx3, dx1.
Huh?
And dx3, dx1 is equal to minus dx.
Yeah, that's exactly the point. We use the orientation again, right? So star of alpha equals beta means alpha wedge beta equals omega. Right? Right? So you have a two form here. You hit, and you're looking for a dual object. So somehow you're looking for one form acting on two forms by wedge product here. So alpha wedge beta equals omega.
Is this the definition of the wedge?
What?
Is this the definition of?
No, we have defined wedge. Right? Wedge is just the wedge in the exterior algebra. It comes from alternating tensor. But the key issue here is, let's look here. Let's look at this one. D, what did I say? This star of this thing, so this is alpha, so let's call the second thing. I think maybe this is what you mean by definition. I'm talking about this thing here. This thing is going to be this. What did I do here? 2. Okay. So, and that's, you see. Okay.
But the problem is that the wedge it maps from the free form to the function, but here you maps it to a one form.
I map, exactly. Oh, maybe you don't like that I call both map star.
They're different.
Yeah, one goes to functions and one goes to, okay, if you like, I'll call one star one, well, I don't know. I'll call the other one moon.
So what's
I don't know, planet.
so what's the definition of
Satellite.
a star?
I just told you the definition.
No,
I just told you the definition. I define it on a basis, and I define it in a natural way using the basis element and the orientation. Didn't I? I mean, if you're a child and want to know how to, look, as a module, the two forms is a three-dimensional module. I've just written down the basis. Sac, 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 three, you see. The one forms is a module, sac, sac, sac. Now these things are isomorphic, and we should find a nice isomorphism depending on the orientation and so on. This is beautiful. This is beautiful. Okay? And the same thing, we have a beautiful mapping from here to here. Okay, so I've defined two stars. I'm just going to call this star. Okay? If you don't mind, star is defined on the entire de Rham complex. It's everywhere. Okay. Now, you're going to get really excited. This is the first time you've really understood something. You're going to understand curl. All right? Well, the thing is that these guys in the applied sciences, they have all these words, and you never know what the devil they mean. So let's put these things on the bottom so we stay out of the way. Curl. Okay. This is a problem. These people really understand the vector fields, and they don't tell you what they mean by curl. I mean, they might even do this, or something like this. Well, here it goes. There, I'm going to define an isomorphism here. Well, how on earth can I define an isomorphism here? Well, vector fields to one forms to two forms. That's an isomorphism. Vector fields to one forms to two forms. I told you how to go from two forms to one form, I could go back.
Not by D, by star.
By star, of course. Yes, D is not yet in the picture. Thank you very much. I'm only going by star. Right? I mean, vector fields are vector fields. Vector fields to one form, maybe if I should have done star the other way around, but I mean, star is an evolution, obviously. It goes, yeah, star, well, it's inverted. Okay. Vector fields to one forms, star. That's this isomorphism.
But how could you know that curl is also isomorphism?
I have not said it's an isomorphism.
If you want to say
I've defined another isomorphism from vector fields to two form. Again, this is important. The first isomorphism, any stupid person can make this. It's just a one form, you write it down, take the coefficients, you get a vector field. Right? This is a slightly non-trivial one. How do I get an isomorphism here? Well, I go to the one form and I take star back. If you want me to write it down and have fun with it, I'll do it. Well,
But then what's the meaning of curl? It could be identical.
I haven't said what the meaning of curl is yet. I've said what this isomorphism is here.
Yeah.
Okay? So I write here via star. That's what Mihai was saying. You just don't get confused with D. Right? How do I do it? I take a one form, take star. Come on. Okay? Now what's curl? You tell me what curl is. It's in that diagram right there. It's D. You understand? Curl is D. Okay? Curl is D. Curl means, how do you get it? You apply, you start here, go to one form, take D, use this isomorphism. That's curl. Okay, now maybe I should convince you that I can even write down curl. Let's do it. It doesn't hurt anybody to do it, okay? Let's write it down. By the way, you should start to get excited here. You should really start to get excited when I tell you this. That's exciting. So from Durham to Maxwell via Hodge. This is nice. It's the British Swiss-French connection. No Germany this time. Okay. I'm very happy I did this. I think it's pretty and it's a very good experience to do this. And keep in mind, the mathematicians, please keep in mind, if you're later professors, you will teach engineering courses, you will teach physics courses, you will teach service courses, all sorts of courses where this language is used. Right? And you really need to know what it means. So let me see if we can have fun writing it together. You're much better calculating than I am, so let's do it together. Let's write down curl of a vector field. Okay. So compute explicitly curl of, now let's just call it in this language F1, F2, F3. This is, okay. So the first step is you start with F1, F2, F3. What did I tell you? You have to figure out what it is.
You have to write it in coordinates.
Huh?
You have to write it in coordinates.
I'll write it, well, if you wish, I'm going to write this next step in coordinates. So this is, in our language, F ddx1, F2 ddx2, F3 ddx3. But in applied science, they would never write that. Let me.
No, but I mean, if you don't write that, how do you differentiate between F1, F2, F3 and the vector fields and the forms? I mean, you cannot differentiate between them.
I don't know, let's see. So far, you're not complaining, right? You're complaining about the future. So all right, I told you what we have to do. This is the thing we talked about. We have to go to a form. Okay? So let me do it. Okay, I did it. That wasn't too hard. Now I take D. No, what do I do?
Yeah, you have to take the.
Yeah, what did I say? I go to a form and I take D and I come back to a field. So I take D. Ready? I can do it here.
But B is not isomorphism.
I didn't say it was an isomorphism. Curl is not an isomorphism either. Come on.
But Hodge is isomorphism.
Yeah, so what? I agree. I haven't used Hodge yet. I'm only going to use Hodge. Watch what I'm going to do. Just watch. Be patient. I identified a field with a form, or one form. I'm taking D to this one form and get a two form. Anybody can do this. Even I can do it. So let's see what this is. I take this. What is the coefficient of dx1, dx2? It's partial f2 x1 minus partial f1 x2. Right? dx1 dx2. Right? Yeah? And now I have to get another. What's the next coefficient of dx1 x3?
Can you please show more? I mean, I don't get why that is.
Huh? What? It's good we're doing it. Nobody gets it. So what?
Can you please show, I mean, I had trouble also in the homework. Can you please show how you really apply Cartan's formula here?
Yeah, exactly.
Whose formula?
You don't use Cartan's formula here?
No, I use nothing. I use how to compute D. In the proof of Cartan's, we defined D by Cartan's formula so that we had a well-defined global definition. Yeah? In the midst of...
You use Leibniz rule. Can you please show it? How you
Yes,
use it?
I'm using Leibniz rule.
Yeah.
That's exactly what I'm using.
Show how you use it? Because
I just did it. Leibniz rule. Yeah, thank you very much. I will use Leibniz. Yeah, that's good. This is exciting today. So, Leibniz rule is it. If you have a basis, this Leibniz rule on this thing is df wedge dxi, right, plus f d dxi, but we show in the proof of this whole thing, this thing is 0, so it's this. Okay, so I apply it here. Okay, so thank you very much. That's what I'm doing here. I'm applying Leibniz rule. Okay. So what else? I want to find out what the coefficient of dx1 wedge dx3, and so that's easy. That's partial f3x1 d, and then minus df1x3, and then the coefficient of dx2 dx3. Okay, I have to get partial f3 x2 minus partial f2 x3. Now just follow me around in my diagram. Where the heck is my diagram now? I want to erase it. Okay. So where am I in my diagram? I start with a vector field, I go to a 1 form, I take D of the 1 form, I get a 2 form. Now I have to go back to vector fields, and in order to do that, the only way I can go back to vector fields is go by star and back to vector fields. Yeah. So I have to go back by star. So here's star. So we had. Now we've applied high, and now I have to tell you what to go back to. Now remember what you do. You have to go back and use the orientation. So this thing will get the 1 form with dx3 here, and will be plus, because dx1, dx2, dx3 is the right order. So let me just write it like that. That's df2 dx1 minus df1 dx2 dx3. That's what I get here. Here, the missing thing is dx2, but I have to put it in the middle, so it's going to get a minus sign. Minus df3 dx1 minus df1 dx3 dx2. And then here, I have dx1 I want to get, but I put it through 2 things, so that's just a plus sign. So it's plus df3 dx2 minus df2 dx3 dx1. And now, what have I done? Sorry, let's find out what I've done. Took a vector field, went to the 1 form, took D of it. I got to realize that in the vector field, I go back to a 1 form and go back to the vector field, and that will be the answer. So that means the curl is now the vector field that I got hope I'm going to write it here in good language. It's going to be the vector field. Well, it's getting complicated. You understand what I'm doing. This is the first component, right? Because this is right, dx1, and I that was great didactics to make that mistake. So f2x3, and now x2 gets hit with a minus sign, so I'll turn it around. df1 dx3 minus df3 dx1. And then x3 is the same. Now, I don't know if you remember these formulas from physics or not. You see these formulas from physics all the time. I can't remember them very well. I always make a sign mistake. But again, you see what we did. We started with the field. We realize it's a 1 form. We take d to the 1 form. We come back to, we have a 2 form. We come back by start a 1 form, take the 1 form to the field. It's called curl. Okay? I think it's a lot easier to say D. Okay? Alright, it seems easier. Okay, we don't have too much more time. Everything's, you see, we start with Durham, and I told you at the beginning we're going to get Maxwell. This is classical symbols from electrodynamics and so on, right? Now, right, gradient, curl, all of that stuff. Any guesses what here is? Everybody knows what's coming, right? Divergence. Okay. Now let me write what divergence is and then tell you how to get it, and then I'll call it quits for the day. Spent a lot of time today on this stuff. It's basically only language, but nevertheless, I think useful. I guarantee you, if you interview for a job, I guarantee you, as a professor or a teacher someplace where you teach engineers and somebody, they're going to say, talk to you about things, you know, engineering stuff and so on. And they say, oh, you're a pure mathematician, you don't know anything. You know what curl is? And I guarantee you 9 out of 10 mathematicians will not. And it's embarrassing. And a lot will not know what divergence is. More will know what divergence is, because divergence is something that's used more often in analysis. Let me just briefly comment on that. Maybe as a homework exercise, I'll give it to you to compute it because you can have it fun yourself. So, how do we compute divergence? So what did I say? Divergence. Okay, what did I claim? Divergence of a field of F1, F2, F3. Well, I have to identify this with a 1 form, and then we start with a 2 form, and D to get a 3 form, and then use the orientation to get a function. Right?
We're given by star.
Huh?
So we're given by star.
I'm not here.
Again, you go by star. You go twice by star. You go from.
How do you get from?
Oh, okay. You mean this? Whether are you complaining? Not
No,
complaining.
I'm not complaining. The last map is also star. That's why.
Yeah, oh, in fact, it is star. Yeah. Sure, I call that star. Yeah, absolutely. Yeah. Thanks. Okay. So again, to identify with a form, take. What did I just do here? Star. If I'd been an idiot here, I'd take D. Right? And then take D again, and everybody's happy. It's 0. So So I want to, this is an isomorphism. These guys keep worrying about what's an isomorphism and what isn't. Star is an isomorphism, right? D is not. It kills a huge amount of things. Right? So star to the 2 form, D to the 3 form, star to a function. Okay? And you will see that this, you can have fun doing this yourself. If I remember, I'll ask you to do a homework exercise. It's very easy. This is a wonderful map. It's this map. You probably are quite familiar with this map. And it really does have to do with how this field is diverging. And curl is how this field is rotating in some sense. So this was a lecture on language, going back and forth. Also for you guys, it's important to know when you talk to mathematicians, they're going to be a lot more happy if you can use the word D instead of the word curl and divergence. And we should know that you're going to be more satisfied with curl and all these other things. But we should always talk. I just went to a lecture of a brilliant Soviet physicist who's now retired from the Landau Institute of Mathematical Physics in Moscow. One of the greatest Soviet physicists. I went to 2 lectures of his. I didn't understand anything. And the reason was he had all this jargon that was in his pictures. Here's a hedgehog and here's this and all this stuff and so on, all sorts of stuff. And he was talking about topological phenomena in physics that I understand very, very well. And I didn't understand one word the guy said. Right? Now that's his fault too, not just my fault. Okay, so try to work on your language. I guess I'm happy you're here.